will kind of guide us to where we go next. All right, folks, we're going to be looking at this PowerPoint here that I've added to chapter 2 that talks about the Arduino student kit. This is not part of your course materials. This is actually material, like when you buy one of these Arduino kits from the Arduino company, where they give you like basically the Arduino, the cables, the connectors, and then they have a little booklet of it, like example activities. That's where this comes from. So I'm borrowing this from them. But what's really cool is they give you kind of a pretty rich set of tools to work with if you're intrigued on doing this kind of stuff. So let's first talk about the device itself, right? And I mentioned this before, you know, our Arduino is this little microcomputer system, and we'll see one on the next slide here. But because of the way it's built, this is really kind of a unique concept. The hardware is not proprietary. So this is kind of unusual for electronics. Like usually if somebody designs like an electronic device, I don't know, think of like a smartphone or a watch or something like that, whatever they did to build that, they don't tell other companies how they did it because they're going to steal their idea and you know, make their own money off of it. That's not how Arduino is. Arduino is open hardware. So that means, okay, this is what we've made. Here's the schematics. It's nothing all that fancy. You can have it too. And then what has happened, on like the one I have in my hand here, is a clone called an Elegoo. And it's a clone of an Arduino built on their schematics. It's a little bit cheaper, but it's built with all the same components and functionally operates the same. So the concept of open source is kind of interesting. It's been something that we've been doing in the software world for a really long time. In fact, the internet and most coding technologies are built with open source software. All right, and then, you know, okay, so if there's open source, what does it mean to be closed source? Well, closed source, a really good example is Microsoft Windows or Microsoft Office. They don't give away the computer code that creates that, because then that creates competition. Conversely, in the software world, we have the Linux operating system where the source code is given away freely. And as a result, we have not only a couple versions of Linux, but we literally have hundreds, if not thousands, of different versions of the Linux operating system, which is kind of mind-boggling when you think about it, right? Because the source code is shared so everybody can use it to build their own, right? And so if you wanted, you could download the source code for Linux and make your own version of Linux if you knew what you were doing, right? The same concept here with the hardware. So normally when you get one of these, they look like this. They're a little, maybe a tad bit smaller than a Raspberry Pi. They don't have all the same connectors. So for example, there's no Bluetooth or Wi-Fi built into this. There's no Ethernet port. It does have a USB jack, and it's an old USB-B type jack as opposed to an A. It's not the flat kind, but the kind of the boxy kind with the cut off corners. There's a power jack and then some pin connectors for hooking up electronics. So this is really designed very specifically to build electronic circuitry and control it, right? The one that we have that we're tinkering with here is this particular model, the Uno R3, right? So that's the one that I'm holding in my hand here, the clone of it. Other things that you usually get inside of the kit include what we call a battery snap. So that clamps onto the top of a 9-volt battery. So that's a very commonly used power source. A breadboard, like the one I'm holding in my hand here. A breadboard is really kind of like a blank electronic circuit board that allows us to experiment with connecting things without having to solder them, right? We just push the pins or the wires into the board and connect them to batteries and see if they work, right? So it allows us to test things. They also throw in some of these other things like a capacitor. A capacitor is a component that stores a little bit of current, basically, and releases it slowly. The other thing that you often use are what we call jumper wires. I don't have any connected to the board right now, but they're wires of like various lengths with little, you know, piece of wire sticking out at the end that you can stick into the board or connect to other devices. There's also the LED lights, these little tiny light emitting diodes. One thing I think it's kind of interesting, and I didn't really realize this about these LED lights, and I'm pulling this one out of the circuit board right now, but as you look at like a lot of these devices, a lot of them will have a shorter leg and a longer leg, right? And that's by design. It's not like a manufacturing flaw. The longer leg is typically the positive side of the circuit, and the short leg is the negative. So that's something to keep in mind. That's kind of a general rule in electronics. They also include a little buzzer, a photo transistor. And so this is kind of interesting because that's basically like a mini solar panel. You know, that's what that is. We also have a potentiometer, which is kind of like, I think of it as like kind of like the like dimmable lights, like the rotating switch, that's a potentiometer, or like the volume control on your stereo is a potentiometer. So it allows various amounts of currents through the circuit. Other things they throw in there are the power leads. So those are ones where you can, they're basically jumper wires, but usually we hook those up to the board separately. Sometimes there's push buttons, resistors very commonly to step down the voltage or control it. You'll also typically get things like motors. So like if you want to connect it to like, I don't know, a robot or whatever, you know, whatever you want to make move or shake or turn or whatever. A USB cable, obviously, to connect it. The interesting thing about the Arduino is we usually use the USB cable not only to send and receive data, but to also power the device, right? Which is pretty common. So like, I mean, we charge our phones that way, right? But we can also connect our phones to our computers or storage that way. One thing that you can often do is you can like usually model like what you want to try to do on a breadboard, or you can actually use a breadboard in conjunction with an Arduino or a Pi. So often these are included together. Just want to show you, this is kind of the anatomy of the system, so I'm going to make that slide just a little bit bigger. So if you were physically here touching the device, this is basically what you would see. This larger thing here, if you could rotate it, that's the USB port. There's also an independent power port, just in case you're connecting the USB to something that's only sending a signal as opposed to receiving power. Because sometimes you have USB sources that don't send power over them. This big thing, this is actually the microprocessor, the microcontroller that kind of runs the whole thing. And then on either end here, you'll see these like numbered pin slots, and there's a series of them on both sides. And those are where we can actually plug in wires or connectors or doodads directly into the system for being controlled. When we do this first little experimental lab, what you'll notice is that there's some LEDs that are already on the system board. So the one is here, number D, which is just the power light. So that powers up when the thing has power. There's also these two right here, listed with B, which are transmit and receive. So when we take and we inject code into the device, it's kind of like the upload download indicators that like, hey, I got the signal, I'm receiving the information, right? And then there's also an additional one here, and I thought it was labeled, but oh, right here, this one marked L. They don't actually have it designated with a letter, which I think is interesting, but it's the built-in LED, and that's the one we're going to play with tonight, because I don't want to get you guys like wiring up circuits. We just don't have time for that. But we are going to get some code injected in here and get that light to turn it on and off. I don't know, it sounds really silly, but the first time I did it, I was excited, you know, because for silly as it is, it's like, hey, I made it do something. That's really cool, right? And it feels empowering. All right, so when we actually get to doing that work, we are going to actually inject a program into it. So how do you do that, right? So first thing, you know, whenever you think about writing computer code, you guys aren't here taking a coding class, at least not yet, right? Like if you're in the cyber or networking or CSS program, eventually you learn how to write Python and Bash scripts and PowerShell scripts to control servers, right? Here we're going to learn a variant of the C language that's designed to control this, right? And you know what? I'm not teaching you really language fundamentals. We're going to take some code that pre-exists and just tweak it a little bit. So there's nothing really to write. The Arduinos do come with their own piece of software. So if you manage to buy one of these devices, you can go to their website and download the piece of software that we'll be using. It's really easy to do, really easy to install. I do have it installed here on my laptop, so I hope to do my demos like right here, hopefully. All right, the setup is pretty darn simple. There's a couple little tips that I can just guide you through. I don't know if these things actually link out, so actually I'm going to follow this link for a moment. So they have their, and this is not how I got to it. Okay, so I just went here, right? So you do your download and they kind of walk you through the process of installing it. Frankly, super easy, but once you get the thing installed on Windows, there's a bunch of like subsystem components you have to install with it. And so it's like really installing like 4 or 5 pieces of software all at once, right? And those extra pieces of software are ones that like control the lights, control the power, control the OS, et cetera, and you have to install them, otherwise you can't use it. So that's just a helpful tip. If you go that far, I don't anticipate most of you will, but you might, The environment that we will work with looks like this, and I'm just kind of showing you a splash screen of it. You'll get hands-on with it in just a moment, and you'll see what I'm talking about. But it's just an environment like this, and it comes with the default program. The one ask that I have from Jerry, who owns some of these devices, some belong to the schools, when we're all done doing our lab today, that we re-inject the original code back in so he doesn't have to wipe it next time. So that's kind of a process that we do. It's kind of like, hey, you can use the tools and do whatever you want with them, just clean them up and put them back when you're done. That's kind of the process. What we're going to work on tonight is just making a light blink. I'll walk you through all the steps. So even though they kind of demonstrated here, they show you all the procedures. I'm hoping I remember all the procedures, but basically what happens is the code that we'll write is basically the code that you see here on the screen, this bottom stuff here. And this code is pre-written, right? So if you can just pull it up correctly and upload it into the device just starts doing that. Right, it's really just that simple, and hopefully we get that far. In some cases, people like to write the code first and then connect the device. I'm going to tell you, kind of functionally doesn't really matter, but we will connect it to any USB port on the computer. It should work, and then we'll go through the kind of the connection steps in the IDE, and I'll show you these. So I'm kind of going through them really fast, but you can follow this PowerPoint if you are doing it on your own. But ultimately, we upload the code into the device, and then the device just performs the action. What's interesting about that is once it's written onto the device, and because of this microprocessors also flash memory, that instruction set stays, right? So if I lose power and then get power back to it, that program's still here. It's not erasable. It's kind of an interesting way that it works. And then, of course, once you get it working, can you figure out how to make it blink faster? So we'll play with that. Then they have some slides here on being electrically safe. The first thing I'll tell you is that because these are low voltage systems, even if you manage to kind of short a connection or something, which you won't do, by the way, there's not really much risk of damage. It's like touching both ends of a AA battery or something. You're not going to die. Right? If you touched a really powerful one, maybe. All right, so that's kind of my quick little primer.